This is Professor Collins again, and today we're going to talk about the material in Chapter 11, Liquids, Solids, and Intermolecular Forces. We spent a good deal of time talking about gases, the other phase of matter, in Chapter 5. I suspect you've learned about the states of matter in several of your science classes. Today we'll try to expand on it and as it relates to chemical matter. Solids, of course, have rigid shapes and volumes. The external shape can reflect the atomic and molecular arrangement. And we understand solids relatively well and their forces that they act upon each other in terms of their molecular forces. We understand those very well, reasonably well. Liquids have no fixed shape and they fill what a container completely, or sometimes they do not. Liquids are probably the hardest of the phases to understand because of the different kinds of forces based on concentrations and other factors. Gases we understand very well, and the reason we talk about that earlier in this class we talked about in Chapter 5 is because they do fit very nicely into laws like the ideal gas law. And this table at the bottom shows you some of the differences in the phases. Of interest to us today in this lecture is the strength of the intermolecular forces. Intermolecular forces between one molecule to another. They're weak amongst gases, which helps us understand gases much better. They're moderate between liquids, molecules in liquid solutions, and they're very strong in solid solutions. And we know, of course, that matter can be transformed from one phase to the other by changing the temperature and or the pressure. Properties of the three states of water are shown in this table: gas, liquids, and solids. Water is a bit unique, as you know, probably, that because the density of the solid form of water is less than the density of the liquid form. This plots what we call a phase diagram, and this is the phase diagram for water. Temperature on the x-axis, pressure on the y-axis. The triple points defined as the point at which all matters exist in equilibrium. For water, you'll note that it's a little bit less than 1 atmosphere of pressure and a little bit above 0 degrees Celsius. Let's define briefly the different forces associated with molecular substances and molecular solutions. You have strong attractions that take place between atoms in a bond. Those are very strong forces. These are called intramolecular forces. They're internal to the molecule, like the double bond in the O2 examples here. So those forces are the strongest by far: covalent bonds, ionic bonds, metallic bonds. Other types of forces can be significant if there are a certain quantity of them around. For example, hydrogen bonds. Hydrogen bonds, dipoles, bonds, dispersion forces are all weak forces, and they're called intermolecular forces. They take place between one molecule and the adjacent molecule. Here are some questions that we can answer by using explanation of intermolecular forces. The first three are about water. Why is it usually a liquid? Why does it boil at a high temperature? Well, to answer those two questions are due to the fact that there's numerous hydrogen bonds that keep the molecules together in the liquid phase. And so it takes a lot of energy to break those hydrogen bonds and convert a liquid to a gas. Why does ice float on water? Because we know water in the solid state has a density less than that of water in the liquid phase. Why is I2 a solid where Cl2 is a gas? Why are sodium chloride crystal little cubes? Answers to all these questions have to do with their specific intermolecular forces. Intramolecular forces, as I said, are the strong forces that hold atoms together in molecules: ionic bonds, metallic bonds, covalent bonds. Intermolecular forces in the focus of this chapter have to do with the smaller forces: ion to ion forces, ion to dipole, dipole, of which hydrogen bonding is one of the more common dipole forces, and a very strong force in its cumulative nature. Dipole-induced, which are weaker forces, dispersion forces, or van der Waals forces. So let's discuss just the relative strength of intermolecular forces. Going from low to high, let's look at the fourth column of strength. The first column and the fourth column, dispersion forces, are what we call temporary dipoles that take place in molecules and atoms. They're very weak. You have dipole-dipole forces that exist between molecules that are a little bit stronger. Hydrogen bonding is a strong type of dipole force because you have hydrogen bonds between hydrogen and either oxygen, nitrogen, or fluorine. And the strongest of the intermolecular forces are ion dipole, where you have mixtures of ionic compounds and polar compounds. Now, an example of the strongest of those intermolecular forces is the ion-ion attraction, such as an example of the lattice energy associated with sodium chloride. You have cation to anion, positive to negative attraction, ordered crystalline structure. It's the strongest and explains why ionic solids tend to have higher melting points than other types of solids, such as covalent molecular solids. In terms of solutions, the strongest intermolecular force is one called ion dipole attractions, and we're talking about permanent dipoles. Dipoles like a solution, aqueous solution, water and sodium chloride. Salt dissolving in water produces the different ions, the sodium cation, chlorine anion, and they have strong intermolecular forces, ion dipole forces that lend strength to the solution. This type of force could have approximately up to 10% of the strength of the actual covalent bond. Dipole-dipole intermolecular forces are slightly less in force than ionic dipole forces, but they do exist in this illustration, or this image to the right, on the right side. Looks like it's of acetone. Acetone has a partial positive charge to the left of the molecule and partial negative charge, as symbolized by the delta plus and minus signs, to the right side of the molecule in the image, where the oxygen atom is. And it's attracted to adjacent molecules by a force. And in a cumulative number, these forces can be rather strong, particularly when we're talking about dipole-dipole bonds called hydrogen bonds. They, of course, are between hydrogen and a very partial negative atom like oxygen, as in the case of water, or it could be nitrogen or even fluorine. All form very strong, relatively strong hydrogen bonds, which are a type of dipole-dipole force. As we noted earlier, hydrogen bonding in water gives water some extremely important properties. Its boiling point is higher compared to other compounds of similar molecular mass. It's a small molecule, so you might expect it to boil normally at the lower temperature. But the hydrogen bonding keeps it from breaking and forces a lot of energy to be put into it to break those hydrogen bonds to convert a liquid to a gas. It has a relatively high heat capacity, and the liquid density of it is greater than its solid density due to these hydrogen bonds. A very weak force, intermolecular force, is called induced dipoles, or dispersion forces. They take place between a polarized and charged particle and a non-polarized particle. These are temporary dipoles, and they exist typically in nonpolar particles, as in the image to the right, which is that of a helium atom. Excuse me, a helium molecule. A helium atom and its neighboring helium atom have temporary dipole-dipole forces. It's important to note that while very weak, these forces allow substances like O2 and I2, which normally you think of as nonpolar, and they are very nonpolar, but they can dissolve in a polar solvent like water because of this dispersion forces, the temporary dipoles that exist. Now, there's a relationship between the shape, the molecular shape of a molecule, and dispersion forces. Because dispersion forces are the weakest of the forces, the more contact spot, the more surface area that the force can be made between one molecule and the adjacent one, the more effect the dispersion has on its physical properties, such as boiling point. Here you have two different alkanes. One's an N-pentane, which is a long hydrocarbon, and that's an A, and B is a neopentane, which is more of a boxy hydrocarbon. And the difference is in terms of surface area, you have large area for interaction in the molecule in A, N-pentane, and than you do in molecule B. So you would expect the small dispersion forces to be higher in N-pentane as you would neopentane. There is also a relationship between the molar mass of substances and the number of bonds or intermolecular forces that take place. The larger the molecule, the higher the number of forces, and the higher the boiling point. The highest on this list of hydrocarbons is N-nonane, which is C9H20, and it has a linear relationship between mass and boiling point, all the way down from C9H20 to N-pentane, C5H12. This slide's identical to the one we saw a few minutes ago. It just summarizes the intermolecular forces and their relative strength and the types. Dispersion, going from weak to strong. You have dispersion. Those are temporary dipoles. You have dipole-dipole. You have hydrogen bonding, which is a type of dipole-dipole. And the strongest is ionic dipole forces. This is an interesting slide showing competing forces in two different liquids. You have water and mercury. Water forms a concave top when it's due to its relationship to the surface of the tube, and mercury is the opposite, convex. The curving of the liquid of water in a thin tube is due to the competition between two forces, between adhesive and cohesive. The meniscus is concave because its adhesion to the glass is stronger than its cohesion to itself. That opposite effect takes place for mercury because mercury has a stronger cohesion to itself than it does its adhesion to the glass. Another property of interest is called viscosity. The viscosity of a fluid is a measure of the liquid's resistance to flow. It is the energy required to move an object through a fluid. So it's affected by two things primarily. One is temperature. As temperature increases, the liquid viscosity decreases. You need more kinetic energy. Viscosity is also affected by the size of the molecule in the liquid. The more complex or larger, the more viscous the liquid is. Solubility and intermolecular forces, they're very important, which helps us to explain why the phrase like dissolves like. Polar solvents dissolve polar solutes. Nonpolar solvents dissolve nonpolar solutes. So we talk about a liquid being immiscible. Immiscible means that nothing is in common with each other. That means that like in the image below, you have oil and water. We know they don't mix, and this is the reason why. One's a polar solution and one's nonpolar. They do not mix. They are not miscible. They're immiscible, and they are not soluble with each other. We spoke of the kinetic molecular theory of gases back in chapter 5. Now we're going to talk about the KM theory of liquids. When you have attractive forces strong enough that the kinetic energy can only partially overcome them, the material will become a liquid. In this liquid, the particles are packed together with very limited rotational or translational freedom. So liquids, unlike gases, are almost incompressible. So we probably don't normally think of liquids this way, but they do have close contact, the molecules do, with one another, hence they are not compressible. But that limits their movement. they do have appreciable intermolecular forces. Polar substances like water will have hydrogen bonding, or other types of polar solutions can have dipole-dipole forces. Nonpolar substances depend primarily on dispersion forces. A liquid's volume is the capacity of the container it is in. Let's talk about two changes that can occur between phases and compare them. Condensation versus vaporization. Condensation is an exothermic process. When water in a gas phase is condensed into a liquid, energy or heat is released. As condensation is exothermic. Vaporization is an endothermic process. Both vaporization and condensation are changes that are affected by the strength of the liquid's intermolecular forces. In vaporization, the weaker the attractive forces between molecules, the less energy is needed to vaporize. In condensation, the weaker the attractive forces, the more energy needed for the vapor molecules to condense. A couple of terms we should be familiar with. Liquids that easily evaporate are said to be volatile. Liquids that are not easy to evaporate are called non-volatile, like water. Recall what vapor pressure is. The vapor pressure is the boiling point of any liquid at atmospheric pressure. At a given temperature, the vapor pressure of a liquid depends on its intermolecular forces. The greater the strength of the intermolecular forces, the more energy it takes, the more that's needed to convert it from a liquid to a gas. Therefore, the higher the boiling point temperature. Look at the curve associated with water, temperature versus pressure. It's 100 degrees at the boiling point at atmospheric pressure of 760 millimeters of mercury, or 760 torr, 1 atmosphere. As I said, a liquid's vapor pressure is a function of temperature. The vapor pressure increases with increase of temperature. On vapor pressure curves, the temperature and pressure are at equilibrium between the liquid phase and the gas phase, but when the pressure changes, then the temperature will change. This means that boiling points of liquids change with altitude. Water boils at around 100 degrees Celsius at 1 atmosphere of pressure, which is where we are in Florida, being so close to the surface of the ocean. If we're in the mountains in Colorado, water will boil at a lower temperature due to the change in pressure. Let's define some enthalpy terms. Delta H of vaporization, delta H VAP, is the amount of energy required to vaporize 1 mole of liquid. It's somewhat temperature dependent. The heat is required to convert a liquid to a gas. It's also endothermic. If it's endothermic, therefore delta H has a positive value. It is referred to as the heat of vaporization, or enthalpy of vaporization. Now, the heat of vaporization is exactly equal in value to the amount of energy of condensation, just with the opposite sign. So the bottom point you see, delta H of condensation equals negative delta H of vaporization. One's endothermic, one's exothermic. On the bottom end of the heating curve, you have similar heats of fusion taking place, but it's not called heat of fusion. Of course, it's called heat of crystallization. The heat of solidification or crystallization, those are synonyms for the enthalpy change, is equal to a negative value, exactly the same value, but with a change in signs of fusion. Crystallization is endothermic, fusion is exothermic. This slide compares vapor pressures and enthalpy of vaporization, heat of vaporization for 3 different substances. H2O has a relatively high enthalpy of vaporization, heat of vaporization, going from a liquid to a vapor. And why is that? Due to the fact that it has numerous hydrogen bonds that require a lot of energy to convert, hence the large value. SO2 has dipole forces within the molecules. SO2, sulfur dioxide, is a polar molecule, so dipole forces exist, it has a relatively high value compared to a noble gas like xenon, where its only intermolecular forces are induced dipoles or temporary dipoles. The heating curve of a liquid is shown in this plot to the right. On the x-axis, you have the amount of heat added and the temperature on the y-axis. And the reaction follows the equation Q is equal to the mass times C sub S, which is specific heat, times the change in temperature. So at the boiling point, all the added energy goes into boiling the liquid. The temperature stays constant during this point. If we're speaking about water, that means water stays at 100 degrees in liquid phase until you've broken all those hydrogen bonds and converted it to a gas phase. Then you can continue by adding more heat. You can continue to increase the temperature up in the gas phase. Again, let's look at the different stages of a heating curve of water. In the first stage, the very bottom, going from below the melting point to the melting point, the ice is warming up in the solid phase, and the equation Q equals M times the specific heat of ice, water in the solid phase, times delta 2. You can calculate how much energy it takes to go, if you know the mass and the specific heat of the solution. For water, it's well known, and the change in temperature. Now at step 2, the temperature does not change, so the energy required to convert the solid to a liquid is shown for water, 6.02 kilojoules per mole. The equation is Q equals N, the number of moles, times the heat of fusion, or the enthalpy of fusion. Fusion is the melting of it. The third stage shows the liquid water warming. Now that's uses in the specific heat in this equation times the mass times the change in temperature, the specific heat of water, which is a known value of 7.53 kilojoules per mole. Stage 4 is when we're at the boiling point. It's when the hydrogen bonds are starting to break to convert the liquid to a gas. Because those numerous hydrogen bonds take a lot of energy, the value of energy at this phase, the heat of vaporization, is what it's called, delta H VAP, is 40.7 kilojoules per mole. Then after you've broken all those hydrogen bonds, you can continue to increase the temperature using the specific heat of water, which is a known value in the gas phase. So in this set of steps, different steps, you have 3 that involve specific heats of solid, that's number 1, the specific heat of water, that's number 3, and the specific heat of gas, that's number 5. Number 2 and number 4 are similar. You're using delta H values. In number 2, you're using delta H, the value to break the solid phase bonds and convert it to a liquid. That's the heat of fusion, delta H of fusion. And step 4, you're using the delta H of vaporization. Sometimes you need to do 5 different calculations to calculate the amount of energy converting a material, water or any other material, from its solid phase to a temperature in the gas phase. So following the discussion of the heating curve in the previous slide, let's do a problem where we go across all 5 steps of the process and calculate the amount of energy needed to convert a substance from a solid below its melting point to a gas above its boiling point. Let's take 1 mole of water starting in the ice form from -25 and bring it up to the melting point. This will be step 1, where we need to use the specific heat of water in the solid phase, multiply it by the mass and the change in temperature, and we get a Q of 0.941 kilojoules. The next step is converting that ice to water, the solid to a liquid, at the melting point, at the 0 degrees. Temperature does not change. So the calculation of energy, heat required, is the number of moles times the delta H of fusion, the heat of fusion, or enthalpy change of fusion. That's how much energy it takes to convert 1 mole of a substance. For water, it's 6.02 kilojoules per mole. If you have 1 mole, then you simply have 6.02 kilojoules of energy at this step. So after the first step and the second step, we have heat in the sum of slightly less than 7 kilojoules. Let's continue this process and do steps 3, 4, and 5. Now we're in the liquid phase. We want to go from the melting point, 0, to the boiling point, or 100. We calculate Q by multiplying the mass. If it's 1 mole of water, it's 18 grams, times the specific heat of water in the liquid phase. That's different than water in the solid phase. And then we multiply that times the change in temperature, which is 100, and we get 7.52 kilojoules. Continuing to step 4, where we're at the boiling point of water, we don't go past 100 degrees. We're just converting it from a liquid to a gas. We have to spend a lot of energy in order to do this because we're breaking a lot of hydrogen bonds that make water uniquely high in terms of its boiling point. Q times N times delta H, vaporization. The heat of vaporization has a value of 40.7, very high. And we end up needing 40.7 kilojoules per mole. For this example, 40.7 kilojoules. By far the largest amount of energy is required in this fourth step. In the final step, we said we wanted to convert it to a final temperature of 125. So we know we're going to be in the gas phase from 100 to 125. Delta T, therefore, is 25. This time we're using the specific heat, C sub S. That is a value for water in the gas phase, all different than water in the liquid phase, different than water in the solid phase. It has a value of 2.01 joules per mole per degree C. And you do this calculation and you get Q equal to 0.904 kilojoules. Let's talk about processes that occur sometimes that bypass the liquid phase. When molecules or atoms in a solid they do have thermal energy and allows them to vibrate. The vibration can be sufficient enough to break from the surface and become a gas. This process is called sublimation. When a solid goes directly from a solid phase to a gas phase, it bypasses the liquid phase, but the amount of enthalpy change, the heat of sublimation required, is the sum of the heat of fusion plus the heat of vaporization. So it takes the same amount of energy, although in practice you don't see it converting from gas to liquid to solid. Simply goes from gas to solid. The opposite often takes place, the reverse, and that's called deposition. It's the capturing of vapor molecules from a gas to a solid. Now we're going full circle from the slide at the very beginning of this chapter showing the phase diagram. Let's determine and answer some problems by determining the phase for the following points on the phase diagram of CO2. Think about each of these for a minute and then look at the answers in the next slide. The answers for this question and number part A, at that temperature and pressure, you have a liquid occurs. You're at the triple point in part B. That's the point at which you have a solid, liquid, and gas in equilibrium. Point C is 10 degrees Celsius, 1 atmosphere. You have a gas. Number D, minus 78.5 and 1 atmosphere is a solid and a gas. You may recognize this in CO2, which is also called dry ice. Perhaps you've seen dry ice in punch bowls. It's a solid when it's at very low temperature, minus 78 degrees Celsius. But as it warms up, what happens? Sublimation occurs. It doesn't turn to a liquid again. It goes directly into the gas phase. In part E is the temperature and pressure point at which a supercritical fluid exists. That's the critical point of temperature and pressure. We've discussed the kinetic molecular theory for gases, liquids, and now let's do it for solids, just real briefly to wrap up this chapter. When you have attractive forces between molecules strong enough so that the kinetic energy cannot overcome them all, then the material will be a solid. In a solid, the particles are packed together without any translational or rotational motion. The only motion that occurs, the only freedom the particles have, is vibrational motion.